Good evening, folks. My name is John O'Rourke. I work as a lecturer in Letterkenny IT, and most of my research work is with Queen's in Belfast, Queen's University. I'm a long-time practitioner in the industry and a relative newcomer to academia, so I'm inclined to be very solutions, practicality, applied solutions-based oriented. In 1996, I was working for a government organisation, and they had a business need to connect to the internet. One of the most senior people in that organisation asked me if I could connect the organisation to the internet, and I said, of course. He asked me if I could guarantee the security of the organisation after that, and I said, of course not. And that remains true in most cases to this day. So, like most organisations, after some prevarication, they bowed to the inevitable, they connected anyway, with the knowledge of the risks and with whatever mitigations they could put in place. Right now and to this day, that remains our relationship with remote connectivity. So the underlying issue is this. For most of my life, this technology has been developing, and it's now incredible. We have incredible perimeter devices, firewalls and the like, with phenomenal technology. The development over the last 20 years has been staggering. But what are these devices? These devices are primarily conventional hardware, conventional operating systems, configured for their purpose very, very precisely. But underlying everything, they're commodity hardware and commodity software. There are applications then that sit on top of these devices, and they have their weaknesses as well. Our perimeter devices are conventional hardware, conventional software with the same bugs and vulnerabilities that exist in any modern hardware. You could say the same of our bastion hosts. So we take a device that's intended to sit in a DMZ that's perhaps going to be exposed to the internet, to external networks. We can harden those devices as much as you like. Periodically, zero-day exploits will show for those, vulnerabilities will show for those, and they will be exploited. Let's go for an axiom at this stage. I'll be brave. Once a network is connected to remotely, it's impossible to guarantee its security from remote attack. That seems to be the case. I'm going to be a little bit unscientific and state that early on. That would be a good cause for debate in the questions. So one of the solutions to this, obviously, is to air gap the network. So if that particular government department had decided not to connect, then pretty much by default, they would have been secure from remote attack, or mostly secure from remote attack. But the functionality then is extremely limited. So what we can do there is take something that's a critical application. Let's say I'm a certificate authority and I want to keep my root certificates in a secure store. I don't want there to be any possibility of a remote attack accessing my keys. Let's say I'm a big Bitcoin miner and I want to keep my wallets, my Bitcoin, everything related to it, I want to keep it offline so I can mine online and then bank everything offline once that's done. Those might be simple examples. Now, it can be a little bit hard to fully secure from remote attack. The side channel attacks have become more and more inventive. So we see side channels via power, via microphones, speakers, all kinds of interesting approaches to side channel attacks. So, you know, accepting side channel attacks and air gap is an effective way for us to secure a network. It does massively restrict the functionality of what we can then do with that network. But there are certainly use cases. So again, late 1990s, we were beginning to change networks from coax to Cat5 to twisted pair cables to fiber optics. And we didn't have buildings that were flood wired. And it was fairly obvious that if we made Y cables, we could actually take maybe 2 nodes and connect them back using a single Cat5 socket. Absolutely not according to the standards, but it worked absolutely fine. So you need 2 pairs for transmit and receive on something like a 100 base TX T2. So you've got 4 pairs. And we could play around with that and take two nodes, connect them back, Y cables at either end. It worked absolutely perfect. It became fairly obvious at that stage that if you just cut the receive wire, that the device was inaccessible. Now, the problem you had with that was that Ethernet's a little bit sensitive to having a carrier. So we've got these TP signals, these link signals that tell us there is an actual good link, that you're seeing the transmit side of another node or a switch. And in the absence of those, most devices don't work very well. You've got to get in the driver level, or you've got to fool it in hardware. But essentially, for a Y cable and something that will produce my link pulses, I can create a device which is completely isolated from external connectivity, where I can send data out. It's absolutely perfect for telemetry. It's absolutely perfect for me, say for metering purposes, for measurements, anything of that nature. It works absolutely perfectly. And I can stream UDP packets out of a device with that device being completely inaccessible from, and completely unexploitable by remote attack. Obviously, I've got things I've got to play with. I've got to manually populate ARP tables. I need to use UDP rather than TCP. There are obvious constraints, but it does work quite nicely. And we had applications where we used exactly that. So that's a production system that's actually working at the moment. There's live data streaming out of that. So, about 2013, 2014, we were trying to secure data streams from synchrophases. So in the power industry, when you're trying to do smart grids, you're trying to look at the state of a network at any particular place. One of the devices we use for that is the phasor measurement unit, the PMU. The protocol, IEEE C37118.2. So what we were trying to do is essentially stream that protocol from substations, being able to absolutely guarantee that the devices were secure. And this allowed us to do so. It's extremely simple. I'm taking a fiber transceiver. I'm fooling the secure side with a cul-de-sac transceiver. I'm telling it it's got a carrier when no carrier actually exists. And then I'm transmitting data out from it. So I have a perfect one-way data flow coming from my instrumentation. What's behind that? There could be an entire subnet behind that. There could be an entire substation behind that. All that's important to me is that I've got a way of streaming out UDP data, telemetry data, that's unconditionally secure. And one of the appendices of the C37 standard allows me to operate in autonomous mode. So I'm not even breaking my standards by implementing this. So there's use cases for this, and for us, it's where we need to be able to guarantee that a site is secure from remote attack or a node is secure from remote attack. Absolutely perfect for instrumentation, and we have very, very many applications where this is the case. The units that I'm displaying are streaming navigation data at the moment. So there are two separate applications running across that. Navigation data is being streamed, and the units behind that are actually the source of that data is secure, unconditionally secure from remote attack. So what we wanted to do is see, was there something less hardware intensive, something maybe more flexible? Was there another way we could approach this? So part of the underlying problem, why we can't secure networks, nodes, devices, part of the underlying problem is that we put data and control signals down exactly the same paths. Folks like Martin Cassander around the start of this century were looking at these problems, and they came up with this concept of SDN, software-defined networking. One of the original concepts in SDN was separate out the data flows from the control signals. SDN has grown to mean a lot more than that now, but that was one of the original concepts. So we thought that that offered great potential for us to actually scale up what it was that we were trying to do. So we can build an SDN network in a very, very restricted way. I place nodes on the network and I set the switch so it propagates no traffic whatsoever. I then use a controller to see what communications is actually occurring from node to node. I can enable things, I can enable everything, and I can characterize the traffic. I can baseline any node. So if I've got a node that's issuing instrumentation information that's running, say, encrypted sessions with SCADA, with a PLC, with something like that, I can characterize that node very easily. Once I've characterized that node and I know what its behavior is in a baseline circumstance, I can program the switch to only allow that traffic. Any other traffic is anomalous, but by default, no other traffic will actually propagate. So I build a network, my critical infrastructure network, with exactly that configuration. Any anomalous data flow will be referred to the controller. So by default, I have IDS, intrusion detection, built in. And by default, that traffic will not propagate any further. So I've actually got, by default, intrusion protection as well, IPS and IDS. This seemed like a lovely, elegant solution for us to scale up these ideas of restricting data flows. There is still an attack surface. The controller is part of the attack surface, as is the switch. So to mitigate that, you're looking at what are the attack paths via the silicon, via the actual data paths, and you're looking at the controller. Most academic work to date concentrates on attacks on the controllers. And when you're actually building production systems, it's quite normal to have your controllers on an isolated subnet. Remove the controllers from remote access and you remove most paths for remote attack. I love the way technology's moved forwards. That switch was something of the order of 80 euros on eBay. It's very, very inexpensive to build the test beds. It's a PoE switch, so 5 Raspberry Pis, 3 B pluses running PoE gives you a 5 Unix servers, 5 Ubuntu 18.04 servers in this case, absolutely perfect for doing test beds and applications. And again, that's a live production system. So there are 2 DNSs, there's systems doing telemetry there. And their communications, the intercommunications between the devices and the communications which egresses from that system are completely isolated, completely characterized, and have implicit IDS and IPS. Use cases for that, that's incredibly flexible in terms of what is possible to do. And so many of the threat vectors, so many of the attack vectors that we examined in conventional LAN technology, we can eliminate using this SDN approach. There are some very lovely, elegant things we can do further than that, though. In a substation environment where we've tried applying this, there's an underlying model-based standard, IEC 61850. Part of what you're doing there is you're getting an electrical engineer to build a substation using CAD tools. They place a transformer, all the instrumentation throughout the substation. But at the back end of the system that they're using is an XML database. And it's very, very clearly defined. There's a very well-defined schema. As adds, moves, and changes occur in the underlying process design, you can extract those in real time and use those to configure equipment, to provision equipment, to configure equipment, and in real time to do adds, moves, and changes dynamically should you need to. Absolutely huge potential. One of the applications we had for SDN was using 61850 as an underlying model, if you like, for a substation, and then doing all of our provisioning directly to SDN from that underlying model. And the objective of that was, apart from all the other threats that we were removing configuration error and devices left at default settings and things like that. We were removing that from the attack model. So the SDN solution was very flexible for us for LAN. Next and final question, I guess, where all our recent work is, can we take an individual node, so an IoT device or an industrial IoT device, an Industry 4 device, can we take something that's part of a critical infrastructure, and can we apply these sort of ideas to unconditionally secure the device? This is our current work in progress. Fundamentally, it's a division of duties. The core device, leftmost on the screen, is where all the processing happens. It's where all the important stuff's going on. So this is where we're taking in information from a process. We're doing whatever we need to do with it. We're putting it into a data packet. We're signing it. We're encrypting it. And we pass that encrypted blob of data via a serial path, or a path that cannot be used for reverse attack, to the comms module. The control of the comms module is via a one-way control path. So again, the comms module cannot pass control signals back to the core module. The comms module really looks after the bottom 4 layers of the stack. So it puts the data in a packet and it sends that data to a destination. Now, what the objective is here is to isolate the device that connects to the public network from the device that does the processing and that has the important content. The comms module is holds no data, holds no keys, holds nothing of importance. Any data that passes through the comms module is encrypted and signed, and the comms module cannot decrypt it and has no access to it. The only thing the comms module knows is it's getting an encrypted blob of data, and it knows the final path that it's going to actually transmit that data to. It has no other information. The comms module is a piece of commodity hardware like any other. If it's compromised, it's compromised. So a denial of service attack is absolutely possible, but there is no attack path between the comms module and the core. This is the concept we have of the software-defined node, essentially a single node where we separated out, if you like, the elements that hold data and have access to the network from the elements that are actually vulnerable to exploiter to attack. So that was the first idea, and that was the start of the concept. There were a lot of components to this. Apart from this very simple idea, there were a lot of other moving parts. I mean, it needs to be part of an overall infrastructure. So we need things like somewhere we need a certificate authority or some way of actually exchanging keys. We need a registry. We need some way of consuming services. So while we were working on this, an initiative emerged called the software-defined perimeter, with a lot of the same ideas. So we stopped working on that particular route, and we're using exactly the same terminology now. So, for instance, we could, sorry, let me jump forward. We could end up with a system where we have all of our authentication services at a single location. The services aren't advertised anywhere. There's no public DNS that tells you where to find these. And all the services use single packet authentication. That is, you can scan my port and my IP address, and I will not respond. You port knock, you send me a single magic packet that authenticates you, and now I allow a session to open. So single packet authentication is a magic solution for avoiding your vulnerability to scan attacks or to brute force attacks on a subnet. Mutual TLS identify both sides of the communication, not just as we do with, say, public key cryptography, where we've got a trusted third party. There probably isn't any such thing as a trusted third party in reality. So what we're trying to do here is isolate our services and keep them in the black cloud. They're not visible from the internet. You need to know how to access them to get in, and then you need all the correct keys to get in and out. Overall, this gives us an infrastructure that has very, very few attack paths from outside. Denial of service is still possible. If somebody sees your packets in flight across the internet, they can still track sources and destinations, so denial of service attacks are still feasible. So one of the things we're looking at adding in now is the IETF's DOTS initiative for signaling for denial of service attacks. So that's a very, very quick description of SD Node. It's several years in development at this stage, and a lovely simple prototype is just a Pi 0 on top for instrumentation, a Pi 3B plus on the bottom, which is essentially the sacrificial comms device that can connect to the external network, in this case via two independent parts, wired and wireless. There are a lot of other concepts that we're rolling into this. For instance, with SD-WAN, there are beautiful concepts for considering for multiple paths, which is the ideal path to use in real time, judging what traffic to send over which path. So they're the kind of other concepts that will begin to roll into SD Node at this stage. So if you like, 3 generations of ideas that we've come through over the last, I suppose 20 years. Simple notions like the diode, which Australian military intelligence began publishing on around 1996. SDN, which is commonly used in data centers, but our concentration was on its application for security. And finally, SD Node, our Swiss Army knife. Any node that we create can have the same sort of reduced attack surface as we've seen with the previous solutions. Thanks very much for your time, folks.
Okay. So thanks a lot, John, for the presentation. We have one question already. So if we were to map your work against the OSI 7 layer mode, it would seem that you are doing something fundamentally different between layers 3 and 7. Would you potentially be able to provide layer 7 APIs that allow existing applications which operate at layer 7 to access layer 3 networks securely?
Okay, potentially I'm a heretic. So my ideas are, I like the TCP/IP model. I'm not a big fan of the ISO model. It was, when it was created, it was a compromise and very much agreed upon by committee. I think we need to review how we treat applications once we get above the communications layers. Once we get above, say, layer 3, layer 4, we need to completely look again at how we do applications. Think about what's important to us with our applications. The integrity of the application. Is there a HMAC in there? Do we know, has the thing been signed in such a way that we know that the packet integrity is good? Have we signed it to identify that it is actually us that's sending it, that it has not been tampered with? Is it encrypted? What's the sequence by which we actually go through things like looking at authenticating and then encrypting? What's the correct sequence in the stack that we should be dealing with that? We've got loads of lovely techniques that we use every single day in data storage for things like forward error correction. There's so many ways that we can recover data should we have data corruption on the fly. Now, in the old days, when we propagated instrumentation for critical sites over RS-232 or RS-422, we were bandwidth constrained, but we're much less bandwidth constrained in many applications today. So, could we have a layer, a data integrity layer, where we can actually recover our data? I'm going to be, as I said, a complete heretic and say that we need to completely look at the way we approach the layers above communication, if you like, the layers that are inside the end nodes. And we need to look at what the modern priorities are for secure, trustworthy, dependable, recoverable. Use any adjectives you like. We need to completely rethink how we do the layers that are inside the nodes at either end.
Okay, so I think Tim, the same person who asked the question in the first place, is suggesting, have you looked at the garrison.com solution, which allows HTTP, HTTPS to be consumed securely?
Sorry, say again the name of?
Garrison.com.
Garrison.com specifically, no.
Okay. And then he also suggests, if you looked at the QUIC protocol, which enables TLS authentication over UDP. And then there is a Wikipedia link in the Q&A if you want.
So when we were working on this initially, we used DTLS. QUIC, no, again, you and on me completely.